In this video we'll be revising electron configuration. So our aims for this video is to revise what orbitals are and what their shapes are, and to work out the electronic configuration of the first 36 elements. That's what you need to be able to do for your exam. So you may be asked to work out the electron configuration of any of the first 36 elements or their ions as well. So at GCSE you learn that electrons orbit the nucleus in shells, and that is true, but it's a massive simplification of what is actually the reality of how electrons behave around the nucleus. And the next step up of the ladder, if you like, is what you learn at AS, and that's orbitals. So what an orbital represents is the probability of finding the electron in that space, and usually we usually set that about 90%. Now theoretically, the electron that is associated with the atom could be found anywhere in space. There'll be a tiny probability of it being many miles away, but 90% of the time it will reside in the shapes that represent the orbitals. And at A level you need to know the shapes of 3 types of orbital. And the first one is the s orbital. And an s orbital is simply a spherical shape. Obviously these would be 3D, but I can't draw in 3D. Well, I'll have a go. No, that hasn't worked. But yeah, so it's a spherical shape, the s orbital. The next one along is the p orbitals, and there are 3 of these in one shell. For the s orbital there's only 1 in one shell. The p orbital there are 3, and they are dumbbell shaped, like so. So you'll get 1 in the x-axis, 1 in the y-axis, and 1 coming out at you in the z-axis. They're all that shape, but they're just in different alignments on the atom. The last one that you need to know is the d orbital set. Now, I said you only need to know 3 shapes, but actually there's 2 different shapes for d orbitals, one looking particularly different from the rest. There are 5 different d orbitals, one that looks like this, so with a dumbbell with a ring around the outside, like so. And then the other 4 look like this, but are different alignments around the nucleus. So for example, you'll get 1 in the xy plane, 1 in the xz plane, and so on. So it totals 5 different orbitals, but those are the 2 basic shapes for d orbitals. There's 1 that is this shape, and the other 4 are this shape. So before we can work out the electronic configuration of any element, we have to have a base knowledge of how many of each orbital there is in each shell. So in the first shell there is just an s orbital, and we call that the 1s, with the 1 standing for what the number of the shell is, and the s standing for what the orbital is. In the next shell, the second shell, there is 1 s orbital, which we will label a 2s because it's in the second shell, and there are 3 p orbitals, which we will call the 2p. Now the reason I've drawn them in a line is because these p orbitals all have the same energy as each other, and so we just draw them in a line to represent that. The reason why that's significant is if we were just putting 1 electron into one of these 2p orbitals, it wouldn't mind which one it was in, because they're all the same energy. However, if we're putting more than 1 in, then something different happens, which I'll show you in a second. In the third shell there is an s orbital, which we'll label the 3s, and there are 3 p orbitals, which again we'll label p, but with a 3 this time because it's in the third shell. Then the fourth shell, we've got the 4s orbital, and then we have some d orbitals, and there are 5 of these. But we don't label them the 4d, instead we label them the 3d. Now the reason for that is because the 4s orbital and the 3d orbitals are very close in energy, and sometimes they swap over in the diagram. Now you don't have to really worry about that, you just need to remember that those d orbitals are labelled 3d and not the 4d. So that is very important for you to remember. Then after that, there are the 4p orbitals, of which there are 3 of them. So say a question asked us what the electronic configuration of oxygen was. The first thing you do is work out how many electrons an oxygen atom has. And if you look that up in the periodic table, you need to look up how many protons it has, and for a neutral atom that is the same as the number of electrons. So oxygen has 8 electrons. And then if you've got a diagram like this, we can work out by filling up from the bottom. So the electrons will always want to be as close to the bottom of this diagram as they can, because these are closer to the nucleus than these are. And we can fit 2 electrons in each of these orbitals. Okay, so we can fit 2 in the 1s, we can fit 2 in the 2s, we can fit 2 in each of these 2p's, and so on. So we fill in up from the bottom, so we can fit 1 in the 1s like that, and 2 in the 1s, and you'll see that I'm drawing arrows that are that point in opposite directions. The reason for that is that electrons in the same orbital will spin in opposite directions so that they can fit in that orbital. We put another one in the 2s, another one, so we've filled in 4 so far. And then, as I said before, if there are no electrons in the 2p orbitals, then the next electron, it won't mind which one it goes in, so I'm just going to put in this one. But now we've already got an electron in one of the orbitals, the next electron will not want to join that electron if it doesn't have to. It can choose either one of these, or it could choose this one. Now the reason why it wouldn't choose this one is because it will then be paired with this electron and they will repel each other. If it chose one of these two, then that won't happen. It won't be repelled, and so it will be, if you like, happier in one of these two. So we're going to put the next one there, and so far we've put in 1, 2, 3, 4, 5, 6, so we've got 2 more to go, so put the next one in the next one along, and now it has no choice but to pair up with one of the other electrons in those 2p orbitals. So to write this configuration out, you do it like this. So you've got 1s2, so this 1 represents the shell, the s represents the orbital, and then this superscript 2 represents how many electrons are in that orbital. So 1s2, 2s2, and then 2p4. And that would be the electronic configuration of oxygen. Now, as I always say to you, that the periodic table is the most useful tool that you have when working out a number of different answers for different questions. And for electronic configuration, it's the same, because the periodic table is designed and laid out so that you can work out, firstly, where the outer electron is in terms of the orbital, but secondly, you can work out what the electronic configuration is of any atom using the periodic table. So, as I said before, in the first shell there is just one s orbital that can fit 2 electrons in, and you can see in this first period here there are only 2 elements. So that represents there is just one orbital, and that is the s orbital. In the next period you will see that there are 2 elements grouped over here in what we call the s block, and that's because both of those electrons will be in an s orbital. It then jumps over to this block over here, which we call the p block, and that's because all of these electrons will be in a p orbital. So you can see we've got 2 here, and we've got 6 elements over here, because we can fit 6 electrons in the 3p orbitals that exist in any shell, apart from the first shell. You see in the third period, the same happens again. You've got 2 elements over here in the s block and 6 elements over here in the p block. And then as we get to the fourth period, you can see we've got 2 in the s block, and then we have 10 elements in what we call the d block. And that's because there are 5 d orbitals, and you can fit 2 in each one, so there's going to be 10 electrons in those d orbitals if they were completely filled. And then we go back to the p block. Now krypton is as far as you'd need to go. You wouldn't need to go to the fifth period. So how can we use this knowledge to work out an electronic configuration? Well, let's choose a more difficult example than oxygen. Let's choose nickel. There's nickel in the periodic table. I've put a square around it. So nickel has 28 electrons, as you can see from its atomic number, its proton number. So if we start from the beginning, we can work out how many electrons there are and what orbitals they're in. So you can see that there are going to be, if we count from the beginning, there's going to be 2 in the 1s orbital. So you're going to put 1s2. There's also going to be 2 in the 2s orbital. So we'll put 2s2. We then go over to the p orbitals in the second period. So there's the 2p orbitals, and again it's filled because we haven't got to nickel yet. So that's 2p6. Then we skip down to the third period. We've got 2 in the 3s orbitals, so 3s2, and similarly 6 in the 3p orbitals, 3p6. Then where this becomes useful is what happens to the 4s and the 3d. Remember that these are d orbitals, they're called the 3d, not the 4d. And you'll see that there are 2 in the 4s, and the 4s get filled up before the 3d. And it shows you that in the periodic table. So these 2 are first, so we go 4s2, usually put this in a line but I have enough space up there, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8. So nickel is the 8th one along, so there must be 8 electrons in those d orbitals, so 3d8. And that will be the electronic configuration of nickel. Now, you can write the 3 d orbitals before the 4s if you want to, but it doesn't really matter, you won't lose marks either way. If you write the 4s first or the 3d first, it doesn't matter. Now if you're working out the electronic configuration of a neutral atom, there are 2 exceptions that you need to be aware of. And those exceptions are chromium and copper. Now the reason why there are exceptions is a little bit more complex than I can go into in this video, but I'm going to show you what the answers are for these 2 compared to what they would be if you went through the normal method. So let's start with chromium. If we work out the electronic configuration of chromium, we'd start with the 1s and fill those up first. So we've got 1s2, so this is for chromium, and then we've got 2s2 and 2p6, 2s2, 2p6. We've then got 3s2 and 3p6, 3s2, 3p6, and you can see that the filling up of these orbitals is straightforward and normal so far. It's the next fill, or the next line, that is different. So normally, if you're working out chromium, you do 4s2, 3d4, but for chromium, instead of filling up 4s2, 3d4, it fills up 4s1, 3d5. And the reason for that is that then all the electrons can be pointing or spinning in the same direction in every single orbital they occupy. So you've got a 4s1 where they can spin in that direction, then you've got 5 d orbitals where also they can all spin in that direction. And that is very stable in terms of an electronic configuration. So the next 2 the next 2 bits we'll add to this are 4s1, 3d5 rather than 4s2, 3d4. For copper it's a similar story, and it's almost identical to chromium other than the numbers in these 2 are different, or rather just this one actually, that the 4s1 is the same. So for copper again we'll fill up, so it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. Then we get to here, we get to this part of the periodic table, and normally it would be 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, but instead one of the 4s electrons jumps in to the 3d, and instead you get 4s1, 3d, 10. So those are the 2 exceptions that you've got to remember for your exam. So the final thing you have to understand how to do is to work out the electronic configuration of any ion of the first 36 elements. So for the elements up here, and over here. That's fairly straightforward because all you would do is take the element and then add or take away the number of electrons that forms the ion. So for example, if you're working out the electronic configuration for O2 minus ion, then you go, well, a neutral atom of oxygen has 8 electrons in, so therefore a 2 minus ion of oxygen will have 2 extra electrons. So instead of putting 8 electrons into the orbitals, you're putting in 10 instead, and so you just write the electronic configuration of neon instead of oxygen, if you like. A more complicated example is any one of the transition metals along here, scandium to zinc. So we're going to have a go at doing iron 3+. So the first thing I'm going to do is just draw out the electron configuration of iron by itself. So we're going to have a 1s, a 2s, 2p, 3s, 3p, 4s, and 3d. And there's 26 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Now, with the transition metals in the D block, when they form ions, they will always form positive ions, and an ion forms either 2+ or 3+ ions. And as I said, we're going to work out ion 3+. When these form ions, the 3d electrons do not come out first. It's the 4s electrons that come out first. Remember I was saying that they are very, very similar in energy, and when they form ions, the 4s orbital is higher in energy than the 3d orbitals, and so they are removed first. So if we've got a 3+ ion, we're going to be taking out 3 of these electrons. So we're going to be taking out this one here in the 4s, and also 1 of the d orbital electrons, and the one that comes out is the one that's paired because that's being repelled the most. That's the one that's most likely to come out. And so if we're going to write the electronic configuration of iron 3+, we would write 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d, 1, 2, 3, 4, 5. We're now going to have a look at just a couple of examples of exam questions they may ask you on this topic. And this first one I've chosen because in recent exam papers, and they'll keep on doing it, they're asking more and more for students to apply their knowledge rather than just to remember stuff. So we'll have taught you how to do the electron configuration of the first 36 elements up to krypton, and that's what's in the specification. But you'll see that this question is asking you to complete the electronic configuration of indium, which is here. I'll just draw a square around. So here's another type of exam question that they could ask you, and here is it's basically the opposite of what you've been doing before. Instead of writing out the electronic configuration from the element or the ion they're giving you, this time you are trying to work out what the element is from the fact that it's a 5+ ion with this electronic configuration. You're working backwards. Now what I would do is to first work out how many electrons this ion has using its electronic configuration. So it has 2 plus 2 plus 6 plus 2 plus 6 plus 10 electrons altogether as an ion. So that is, if you add 2 to 2 to 6 to 2 to 6 to 10, that adds up to 28. Now if it's a 5+ ion, that means it's got 5 less electrons than it would have if it was just a neutral atom. So that means that the neutral atom of this element would have 28 plus 5 electrons, which is 33. Now all you've got to do is look in the periodic table and see which element has 33 electrons as a neutral atom. And remember, the number of electrons is the same as the number of protons in a neutral atom. So if you just look at the bottom number and see which one's 33, you'll see that arsenic has 33 protons and therefore also 33 electrons in its neutral atom. So the answer to this question would just be AS. If you have any other questions on electronic configuration, then please come and find me at any time.